Hello everyone, this is Ritika Jain and I welcome you all to my presentation on efficient sleep scoring method using visibility graph and temporal features of single channel EEG. Now this gives an outline of my presentation. So first of all, I'll provide an introduction followed by the data description and then methodology, results and discussions, and finally the conclusion of my presentation. So sleep is not just a continuous block, rather it is divided into several stages and each of them have a particular distinct signature of its own. So three broad stages are wake, REM and NREM, where REM stands for rapid eye movement and NREM is non-rapid eye movement. REM actually is considered to be a paradoxical sleep stage because in this stage the eye movements happen and the brain is more active just like in the wake stage. So there is this rapid movement of eyes, however the eyelids are closed. Whereas NREM is a deeper stage of sleep and it is further subdivided into N1, N2 and N3 stages. Now traditionally the way sleep staging is done is by expert scoring, but it is very time consuming, expensive and a tedious job. Plus it involves a lot of subjectivity, so it suffers from this inter-rater variability. Hence there is a need of a reliable and automated sleep stage classification which can replace this manual scoring system and thereby reduce the burden of these experts. So in this work we have proposed a scoring method for the identification of different sleep stages by using temporal and graph based features from a single EEG channel. Now let me tell you briefly about the visibility graph. So this visibility graph is basically used to characterize a time series by a graph. So as you can see on the right hand side, a time series has been converted into VG where each of the values of the time series are represented by the bars and amplitude is actually shown with the height of these bars. And the connection is with the help of this visibility criteria, which is just based on a simple notion that if a particular node, which is every point on the time series, is able to see other node or it is within the line of sight of that node, then those two will be connected and hence considered as visible. And on the bottom you can see its corresponding visibility graph is shown. Now, the features that we have extracted from visibility graph are mean degree and degree distribution, where mean degree just represents the mean of the degrees of nodes. For example, if you see node number 2, so it is connected to 5 other nodes. So it has a degree of 5. So by degree I mean the number of links or edges it is associated with. So here the degree of node 2 is 5. Similarly, we can generate a node sequence, a degree sequence for each of these nodes. And finally, taking the mean value of those degrees will give the mean degree. And the degree distribution is basically just the distribution of the degrees of the nodes within that graph. Now, apart from the visibility graph features, we have also utilized temporal features, namely autoregressive model parameters, Zod parameters, Higuchi fractal dimension, and multi-scale entropy. And we have chosen these particular features because they have shown outstanding results in our previous works. Now this gives an idea of the dataset that we have used in this work. So we have used expanded sleep PDF dataset which is publicly available on Physionet. We have considered 20 subjects and we have used PZOZ EEG channel. So there are 2 EEG channels and 1 EOG channel in this dataset. However, we have utilized only one EEG which is PZOZ. FPZ-CZ is another EEG channel, but the performance of PZOZ is way better than the FPZ-CZ channel, and therefore we have used only this channel. The epoch duration is 30 seconds, which is standard in sleep staging process. Scoring rules are RNK, which is the ground truth that is available in this dataset. There are 6 different sleep stages: wake, S1, S2, S3 and S4, which are all belonging to the NREM stage of sleep, and the last one is REM. Now this table shows the epoch distribution of the different sleep stages, and so there are total 54,416 epochs corresponding to the 20 subjects. Now this is the methodology of the proposed method. So first of all, we have filtered the raw EEG signal in the frequency range of 0.5 to 49.5 Hz, followed by the segmentation into 30-second epochs, and then we have extracted the features that I just mentioned in the previous slides, which are time domain features and the graph-based features. Finally, we utilize Kruskal-Wallis test for statistical significance of the features, and for classification, we have used RusBoost, which stands for Random Undersampling with Boosting Technique. And this particular classifier has been chosen because it is able to deal with the problem of class imbalance, which is very much prominent in sleep staging problems. Now this just explains the flow chart. So as I mentioned, first of all, we have given a single channel EEG as input. Then pre-processing involves the bandpass filtering, for which we have used Butterworth filter, bandpass filter, and the frequency range is 0.5 to 49.5 Hz, followed by the feature extraction, and then we have fed the fusion of all these features together to a classifier, which is RusBoost here, and then finally in the output we get multiple sleep stages, or in the form of hypnogram, which represents the discrete sleep stages out of the raw input EEG signal. So this is the whole flow chart. Coming to results and discussion. So this plot actually shows a log-log plot of the degree distribution, which is one of the features that we have used across the 6 different sleep stages for a particular subject, and it is plotted as a function of the degree of nodes. So we can see that as the degree of the nodes increases, it becomes less and less likely for the degree distribution. And also we can notice one thing, that here the value of degree of the node, which is k, is taken from 2 to 6, which is sufficient for distinguishing between different sleep stages. So we have utilized only the top 6 values of the degree of nodes to calculate the degree distribution. Now here on the left hand side, you can see that the box plot of the mean degrees for different sleep stages for the same subject which was shown in the previous slide is presented. Now as we can see that the mean degrees are quite well separated across the different sleep stages, and as the sleep deepens, like it moves from S1 towards S4, the mean degree also increases, and it is least for REM across all the sleep stages. However, the wake has the least mean degree. So this is also one of the feature that we have extracted from visibility graph. Now coming to the right hand side, it shows a confusion matrix along with the sensitivity and specificity value for the 5-state classification. So we can see that here it is well able to provide good sensitivity and specificity for all the sleep stages except that of N1. And in literature also we have seen that most of the time N1 or S1 sleep stage is the one which is very difficult to accurately classify, and hence it shows a very low sensitivity value. Now this shows a 5-state hypnogram of a subject, and the top one shows the hypnogram which is generated by the proposed method, and the bottom one is by the experts. So as we can see that overall the pattern resembles a lot. However, there are some spurious jumps, especially at the transition from one sleep stage to another. And this is the reason for some of the misclassifications which are occurring at the transition stage. Now this shows a comparison of the classification accuracies for different N-class classification problems where N varies from 2 to 6, and we have compared it with the existing literature. So here we have used 2 different validation techniques. One is 50% holdout and another one is 10-fold cross validation. And we can see that the 10-fold cross validation accuracies are in the range of 91 to 97 for n equal to 6 to n equal to 2, and it clearly outperforms most of the existing studies. Whereas in case of 50% holdout, very less In fact, here none of the studies have reported 50% holdout, which is a far better validation technique, because here some of the subjects, especially this 50% of the subjects, are considered as a training, and rest 50% are left out as test subjects. And this is repeated for multiple trials. And here we have considered 10 such runs. And the value ranges from 86% for 6-state classification to 94% for 2-state classification. Now, coming to the conclusion. So, as I already mentioned, that we have achieved a high cross-validation accuracy ranging from 91 to 97% and kappa value of 0.82 to 0.94, which shows a very high agreement between the score by the experts and that of the proposed method. Also, this work has focused on utilizing a single EEG channel and minimal set of features, that is 4 temporal and 2 visibility graph. So this method is able to provide very reliable performance with both cross-validation as well as 50% holdout validation techniques by utilizing very small set of features. This method, however, suffers from a low sensitivity value of S1 stage, as I already mentioned, and it mostly gets misclassified as wake or REM because of its similarity to these stages. Thank you so much.